Okay, so this time I'll be talking about attention. Some of this is similar to what was written in the materials, and there I'd like people, I'll just summarize quickly and have people ask questions if anything was unclear. A lot of this stuff is new. The reason why this is new is because since I created those materials 6 months ago, a lot of stuff has changed in in neural networks for NLP. So there's a lot of new material as well. So as I talked about before, we have these encoder-decoder models where we have the encoder and the decoder, and they basically kind of pass their information through this state over here, which we hope will contain all the information about the source sentence. But as Ray Mooney says, you can't cram the meaning of a whole bleeping sentence into a single bleeping vector. And but what if we could use multiple vectors based on the length of the sentence? So if we don't have this, but instead have this, then this would be better. So that's the general idea of attention, which I think you read about in the course materials. Another way to think about it, which I might have talked about in front of a lot of people in this room, but maybe not everybody, is if you think about asking a translator to go and translate a sentence and say, please read this whole sentence, remember it, and then translate it. That's very difficult for them to do. But if you tell them, you can read this sentence, and then you can go along and translate while rereading various parts of the sentence, that's a lot easier for them to do. And that's basically what attention is doing. It's allowing you to look back at the sentence every time you translate a new word. So the way attention works, the basic idea is we encode each word in the sentence into a vector. And when decoding, we perform a linear combination of these vectors weighted by attention weights. And we use this combination in picking the next word. So an example of this is, let's say we have our source up here. This is these are our source sentence encodings, maybe run through a bidirectional LSTM or something like that. Then on the bottom left, we have the decoders. So, and this is our current state, and then maybe we want to decide which word comes after hate. And then we have something called a query vector, and then we also have key vectors, which are these things up here. This is different notation than I used in the materials, the reading materials, but I really actually like this notation quite a bit. So I'll be using it for the rest of the explanation of the slides. So basically, we have a whole bunch of keys. We can kind of think of it as a database or something like that, where we have keys that we use to query and try to find, or we use a query, we try to locate keys that match this query. And then based on that, for each query key pair, we calculate a weight. We run these two vectors through some function and get weights. These can be any real number, basically. And then we normalize these to add to 1 using a softmax function. So then once we do this, we get things between 0 and 1, and they add up to 1. These are basically they look like a probability, but attention is not really a probabilistic variable. It's more just, it's a deterministic variable, but it's normalized to look like a probability between 0 and 1 and to add to 1. And I'll talk more about that later when I talk about other varieties of attention, but that's one thing to remember. So then once we do that, we weight all of the vectors. We can also call these vectors value vectors. So these vectors are the vectors that we're going to want to weight together and combine into a single vector. You'll notice I used a different name for these two, which I didn't do in the reading materials. So in the original attentional model, the key vectors and the value vectors were both the encodings of the source, but there's no reason why they need to be. You could also use different ones. And some recent work has used different vectors for these two. Specifically one paper that I'm going to talk about in detail later. And then you can basically use this attention in any part of the model you like. There's no restriction to how you use this, this weighted attention thing here. It's very common to feed it back into the decoder. It's also very common to use it to make your prediction of the next word or action or whatever. And here is a graphical example. So this example, this is an example of translating Japanese into English. So you have a weighting over the Japanese, and every time you translate a word into English, you get something basically that adds to 1, where white is the brighter one. And then for could you recommend, it's focusing on the Japanese word for recommend. In inexpensive, it's focusing on the Japanese word for inexpensive, and then restaurant, it's focusing on the word for restaurant. And there was also a part in the reading materials on attention score functions. I'm going to overview them here because I'm also going to introduce a new one that was proposed recently that wasn't included in the materials, but seems to make a lot of sense to me. So here, Q is the query and K is the key. And the kind of original way of doing this is the multi-layer perceptron, where we concatenate the query and key together. We run them through one layer of a neural network, and then we multiply this by a vector to get a scalar for each word here. My personal experience with this is that this is flexible. It also tends to be very good. It's usually the best, or it's very often the best option when you have lots of training data of the various methods that I've tried. The second one is bilinear. So basically the idea here is we multiply K by a weight matrix and take the dot product with Q. This has been proposed, and some people have used this before, but I don't see this being used widely in sequence-to-sequence models, and I myself have not gotten as good results with this as others. Then another one is the dot product, where we simply take the dot product of these two. This has no parameters, which is a good thing, especially if we're training with very few data. But it also requires the sizes of the vectors Q and K to be the same, which means we kind of have to restrict our models so that this is the case. So my personal experience with this is this works pretty well when you have small data, but as you get to larger data or larger networks, it doesn't do as well as the multi-layer perceptron method here. But there's one explanation for this, which was just proposed in this paper, recent paper. This is the scaled dot product function, and basically the problem of the scaled dot product of the regular dot product is as the dimensions get bigger, the value of the dot product will also tend to get bigger, right? So if we have the same range of values for each. A vector of 128 times 128 versus a vector of 256 times 256. The dot product of this will tend to be twice as big, right? Now, if we think about what happens, and we have scores of 1 to 0, versus scores of 2, 4, 0. Coming into our attention, after we take the softmax, what this is going to look like is this is going to look like something like 0.25, 0.7, 0.5, 0.05. So it's kind of going to be focused on the middle one, but not very sharply. But if we double this, this is going to become 0.9, 0.09, 0.01, or something like this. So these numbers, I completely made up these numbers, these actual numbers, but the idea is if you have a bigger scale in your in the inputs to your softmax, you're going to get a much peakier distribution. And this is something that you need to be aware of in general. So the idea of the scaled dot product is that the dot product will suffer from differences in how it behaves based on the network size. So the way they fix this is just by scaling by the size of the vector. So if you look at the size of the vector k, they reduce this value by the square root of the size of that vector. And I have not actually tried this myself because I just read about it about a month ago and I haven't done this, but this seems like it makes a lot of sense. So I think this is one attractive alternative to multi-layer perceptron or something like that with no parameters. So are there any questions so far? I think a lot of this was in the reading materials except the last part. If not, we'll start out with our code walk thing, which Dan will do. And this is very much based on the code walk from last time. To do that. Yeah, you go here, press escape.
Okay.
And then move this over. Yeah.
Oh, thanks. So, yeah, is this big enough for everyone to see? In the back, you can see it. Okay, cool. So for attention, a lot of it's going to look the same as the encoder-decoder, like Graham said. And this time we're just doing batched attention because it's a lot faster. And after you've already seen the encoder-decoder non-batch to batch, there's really no reason to look at the non-batched attention. So you load in all the data, you do the same thing for batching as previously. Then you have a few more parameters. You have the size of the attention parameters. And in this case, we're doing the multi-layer perceptron score function for our attention. So if we come over to calculate the loss, well, let's copy this first. One other difference is instead of using just a single directional LSTM like we did in the encoder-decoder, we're using a bi-LSTM over the short sentence. So you run the LSTM over the source sentences, and you concatenate the forwards and backwards representations of the output from the bidirectional LSTM. You feed that into... Then you can use this to start trying to calculate the parameters for the attention. This fixed attentional component and the source output matrix are both going to be used. So calculate those. Then the rest of this here is pretty much the same up until you get to the decoder.
So let me add one thing about this.
Yeah.
This is actually this is a really nice trick. So if you remember, one of the efficiency tricks that was mentioned when Taylor guest taught the class is that we want to cache, or we want to do as few operations as possible. And what we're doing here is basically, when we do the multi-layer perceptron attention, we take in the source, and then we take in the key, and we also take in the query. And this is maybe W1, W2. And then we run this through a tanh function.
In this case, I'm kind of doing them.
Okay. I think you're caching this, right?
Oh yeah, those try it.
Yeah. So the this thing here, the key, only depends on the source. It doesn't depend on decoding the target or what your next target is. So basically, you can cache this at the very beginning of processing the sentence, and this will make things much faster. So the alternative would be to recalculate this every time you decoded something in the output. But that would be, this is a big calculation here, so that would be inefficient. And by doing this, you can do this significantly more efficiently. So if you are interested in this and making it faster, you can take a look carefully at what's been done.
Okay, thanks, Graham. Yeah. So you start to decode the sentence more or less the same as the encoder-decoder model, except for when you get the output of each step from the decoder, you're going to do attention instead of simply feeding this through a softmax and getting the maximum word. So for attention, now we're going to come back up here and look at the multi-layer perceptron. So these are the 3 parameters for attention, essentially. Then we're going to, what Graham said here, where we already cached this here. So we'll add that to the target output embedding, which is the query and the word. Then multiply, take 10h, multiply by the other parameter. And this gives us the output from that. So you can simply take the softmax over that to get the alignment. This was the series of squares. And multiply that by the source output matrix gives you the output from the attentional system, which we're going to use to calculate the final, what did I do? The final softmax. So back down to when we're running through the sentences. We get the output and the alignment. I'm saving the alignment so we can visualize it at the end. Then you run this through, I guess one thing to note is when we're doing this, the output is going to be not quite the same size as the hidden layer. So to make it the same size, we first feed it through an affine transformation to get this middle expression, which makes it the same size as the hidden layer. Then we can feed it through the same affine transformation we use in the encoder-decoder to go as the final function to pass through the softmax. We do pick neg log softmax, and then this trains as normal. Generating is similar, except, I guess that was generation. Yeah, here. So we get the output, then we're doing the same masking as we did before for batching, where you multiply the mask by each of the sentences to delete all of the padding you put on the input sentences. Then for generation, we don't have that. Instead, we simply choose the argmax over all the probabilities of the words in a sentence. Then finally, I also included a little function to plot attention. So this gives us the diagrams that Graham was showing earlier, or something close to that. So after you're done training, you can save your attentional matrices, plot the attention, and look at how they're aligning the words in the sentences. Questions? Anything you want to add?
I wanted to add that I tried plotting the attention. I tried plotting the attention for this, and it doesn't look very good. I think it's because our training data is extremely small. So probably don't. You can try to plot the attention, but it will probably look pretty bad just because the training data is not large enough. But if you use it with larger training data, it should work okay. And any other questions about this? Or? No. Okay. So I will continue. Yeah.
A question on what's the intuition behind modeling keys and queries and language?
So the intuition behind the naming is basically, you can think of it, another way you can think of it is like a relational database, where you have a query which is like select X from Y where Z, or actually let me rename this. It's select V from select a V from database where K equals Q or something like that. So we have this database where we have key value pairs, and we're selecting ones where the key matches the query. But attention is kind of like a soft select. It's not selecting with a 0-1 value. It's selecting based on a kind of like soft matching between the key and the query, and then you add everything together. So I think the intuition behind why we named them these ways is because why these have been named these ways is because from this like relational database. Does that kind of make sense? Or?
What is the reduced value? You compute the attention scores and you reduce the encoder state?
No, the query is the decoder state. The reduced value is the result of the attention. It's often called like a context vector or something like that. And that is it's just a sum over the values weighted by the attention. Yeah.
In the scaled dot product attention, why did you normalize by just one of the fact?
Well, because it's dot product, they have to be the same size. So you don't. If you normalized by, it's as simple as that.
Yeah, I saw this notation in the memory network. Is there any relationship?
Yeah, so a memory network is very similar to to attention. A memory network, there's multiple types of memory networks. So it's really difficult to say exactly what the relationship is because, but basically the idea of a memory network in kind of the original papers is you have this really, really big thing that you want to do attention over. But you have many of the values in your attention be 0. So it's kind of like sparse attention, I guess. Where only some of the values are non-zero. In the original paper, but there might be, there's also fully differentiable memory networks and other things like that. So as I said, there's so many varieties of memory networks, it's kind of hard to answer that question precisely. Yeah.
Reading attention was very explicitly tied to translation. Can you talk a little bit about attention in the context of other NLP tasks?
Sure. So attention can work for anything. Actually, I'm going to give a lot of examples, so maybe I'll wait until after the examples to answer that. Okay, I'll move on to the next one. So that's exactly what I'm going to talk about next. So hopefully it will be clear. So there's a lot of different things that we can attend to. There's a lot of different things that we can pay attention to. The most common one by far is attending to something like an input sentence. So that was exactly what I used in the previous explanation. We have an input that we would like to translate into something else. We can attend to this. It's also very common to use the attention more directly over the input sentence. And one way you can do that is with unknown word replacement, which I mentioned in the reading materials. Basically, the idea here is then there's a thing that takes it a step further and uses it not just for unknown word replacement, but actually for copying words directly into the output. So the idea is that you have either a generate mode, which is on the left side, where you can generate the left side of the top right of this slide, which is where you generate normally, like you would in a normal sequence-to-sequence model. Then the one on the right is a thing where you can basically copy a word from the source. So why would this be useful? Let's say you want to do summarization. If you want to do summarization, the great majority of the words are going to be the same as the words that were in the source. And because of this, you would really like to have the ability to copy words directly from the source and use them in the output. Another one, we have a paper where we extended this a little bit to make it so you can't, where you don't only copy, but you can also basically translate words that are in a lexicon. And this is pretty useful if you have like a dictionary of words that you want to be translating or something like this. These are a couple examples of how you can use attention to kind of copy words or make a more direct connection between the source and the target. So what other things can you attend to? Another one is previously generated things. So what I mean by this is, let's say you're generating something from a language model. You can think that because I've already generated a word once, I'm very likely to generate it again. So if you think about it intuitively, I've said attention about maybe 50 times today, right? So because I generated attention already, you know that I'm probably going to say it again and going to continue to say it many, many times. So the idea here is basically that once you've generated a word, you attend to that word. You attend to the words you previously generated and decide whether you want to copy them or not. So this is kind of an extension or a different variant of the copying mechanism that I just explained before. You could also use this for translation or dialogue generation if you wanted to as well. One thing to be a little bit cautious about this is this was also known as a cache model before neural networks were widely used in language modeling. And in cache models, basically you remember words you already generated and generate them again. These seem to give you extremely good perplexities because or extremely good language model evaluation scores because they give you words you've generated already. But when you actually try to incorporate them into a speech recognition system or something else, what happens is you make a mistake once, then you make the same mistake over and over and over again because you've remembered that mistake. So just because you see good perplexity numbers from a model like this doesn't mean they'll actually be useful in real systems. So another thing, you can also attend to you can attend to both the input and the previous output. So if you've already generated some output, you can also do attention over the output that you've already generated. This is not directly copying this here. This is instead just attending to the words you've already generated. This might be even more useful. And in a way, this will help you precisely remember what you've already generated and then use that information when you generate the next words, for example.
You said about repeating the mistake.
Yeah.
Because you're attending to the
Yeah.
original.
Yeah.
I think I saw some of them, some of words that I don't remember exactly, but because you attend to the generated ones, you don't repeat the same words.
So for the second work here, that's definitely possible. For the first work, this is more focusing on copying previous words. So for the first one, that would probably be more of a problem than the second one, where it can learn to be more flexible, I guess. But the problem is, which I'll talk about next time, is if you're only training on correct output, all repetitions will be correct repetitions, right? But if you're actually working in a place where you might have made a mistake before, you'll also learn to repeat the mistakes. So ways to fix that we'll talk about next class, I guess. So you can also attend to various modalities. It's very common to attend to other things. Images is one example. In fact, when you attend to images, you get these very beautiful heat maps over the image showing you which part of the image you're attending to. And you can say a bird flying over a body of water where you can see it's focusing on the bird to generate. It's also common to attend to other things like speech if you're interested in speech. One of the interesting things when you're doing things with speech is that speech often has lots and lots of frames and you kind of need to reduce, or speech utterances tend to be very long and you kind of need to reduce the length of them. And there's a lot of tricks that you can use to kind of reduce the length when you're doing attention. One thing I should mention is that attention doesn't work if you have, or at least without a lot of work, it doesn't work when you have a really long sequence because every time you have this quadratic, or every time you need to process basically everything in the input sequence. So one place where you might not want to use attention is when you have a really long sequence that you'd like to summarize and then process efficiently. That being said, reasonably length sequences like the ones we see in NLP are usually okay. But even if you want to go from like words to characters, for example, this is something that you need to think about. You can also attend to hierarchical structures. So this is an example of a paper where they do document classification, where basically you encode the words first, or you encode the words of each sentence first, get a representation for that sentence, and then encode the representation of each sentence. Another way you could probably do this is by using a similar style of kind of reduction of the length like they use in speech or for characters or something like that. But this one is doing it sentence by sentence on the sentence level, which seems to make maybe more sense from the point of view of coherent semantic units. Another interesting thing is that you can attend to multiple sources. So let's say you have two varieties of information that you would like to attend to. One example of this is, let's say you wanted to translate from French and German into English. This doesn't seem like it would be a situation that comes up very often, but if you think about it, there are things like TED Talks that have already been translated into 20 languages, but you always want to add one more language. And in this case, you could attend to all 20 languages when you generate your output to get the 21st language. And that's actually a pretty realistic scenario. There was a nice paper recently that compared multiple strategies for using this multi-source attention. The interesting thing is they actually did something like this, hierarchical, where you basically attend to one sentence in one language, another sentence in another language. Then you attend to the vectors that you got from attention, and that seemed to work best for them in this particular task. Another example is, let's say you want to translate, let's say you want to do translation, but you also have a context where you, a visual context. So you can imagine an interpreter walking through a real life scenario where they're looking around, and they can use the information that they see, the visual information, to help them translate more accurately. This particular paper allows you to do this. I'm not actually familiar with the dialogue literature, but it seems very natural to also do something like this for dialogue. So, in dialogue, you're grounded. You could be in a specific scenario or something like that. So then you would want to attend to the things you see in addition to what the previous person talked about. One other thing that I'm going to talk about in a bit of detail later is intra-attention or self-attention. These are two names basically for the same thing. The idea here is that each element in the sentence attends to the other elements. So why would you want to do this? The reason why you might be interested in doing this is, let's say we have this as an example. What we can do is we can basically, when we calculate the embedding for this, we can attend to all the other embeddings in the sentence. When we calculate the embedding for is, we attend to all the other embeddings in the sentence. And the same in an example like this. So these are exactly the same sentence, but basically what they're doing is they're learning to be context sensitive as opposed to context insensitive. This might look like something else that you've heard about before. Does anybody know what this sounds like? Alignment. It's like alignment, but this time we're actually looking at the same word. So attention is like alignment in a way also. Any other ideas? What's that?
How does this differ from the variety thing?
this is different in goal from the Mirity thing. The paper on basically attending to yourself when generating the next word. The idea behind that was to make the prediction of the next word more accurate. This one is to add some context to the word embeddings, basically. Any other ideas? Word to vec? Yeah, you could think of it that way. This is really interesting. These are not the not the answers I was expecting, but they're good answers. So word to vec also is looking at the context around it and using it for prediction and trying to match the context together.
I mean, the equation's not the same, but
Yeah.
convolution has a similar.
Yeah, so convolution is a similar idea. The one I was actually aiming for was if you think about a bidirectional LSTM for the, if you think about what we use a bidirectional LSTM for in the attention, basically that's to incorporate word information about the surrounding words into your word embeddings. So this is doing something very similar. It's incorporating information about the surrounding words in your word embeddings. The main difference here is that there's, I guess, two differences. One is that this is much more direct because you're looking at the word embeddings for all of the remaining words in the sentence directly instead of taking lots of steps through a recurrent neural network. The other reason why it's a little bit different is this is way, way faster because you can do this with like a single matrix multiply, which is super fast compared to running an LSTM over your entire sentence. Okay, so let me go back to answering the question about how does this relate to other NLP tasks. Basically, you can use attention in any, you can use attention in almost anything where you have a sequence and you would like to use that sequence to make some sort of prediction. One example of this is you can use attention in parsing. So you take in a sentence and then you want to generate its parse tree. So you generate its parse tree one by one by taking an open bracket every time you open a constituent, close bracket every time you close a constituent, and then the word every time you generate a word. You can do it. You can use it for lots of other tasks as well. But basically, anytime within a particular context you want to find the appropriate things to focus on in the input sentence, you can use some sort of attention mechanism in your model. And it's probably the case that somebody has tried that for most major tasks. Does that answer the question? Or? Yeah.
So in this case, does the word have multiple encodings depending on the context? Like what is the task? What is the
So basically, you could think about, yeah, I don't actually have an ambiguous word in here, but if I had added an ambiguous word like bank, if you think about bank will basically have a different sense based on the other words in the sentence, right? So if you have money or corporation or something like that, bank will probably be the financial bank. But if you have river or something like that, it will be a river bank. So what it could do is basically it could learn, when it learns the embedding for bank, it will put 50% of the weight on bank, or maybe 60% of the weight on bank, and then 30% of the weight on river. And then the linear interpolation of river and bank will become the embedding for that word for downstream processing. So yeah, that's the idea behind this. Yeah.
Does this still use a recurrent layer to encode?
It doesn't need to. So you could have a recurrent layer before you do this, or you could have no recurrent layer. Actually, the case study I'm going to talk about at the end uses no recurrence whatsoever. And it still can do interesting things. Yeah.
But then doesn't it lose the order information?
That's a good point. I'll talk about that later. Yeah. Yeah.
a question about the multi-attention?
Yeah.
So the assumption is that there is a single latent representation of which has generated all these different sources,
Uh-huh.
and we are trying to attend to each one of them. Is that
Um,
is the assumption right?
Basically, in the end, you will need a single vector. One way you can get the vector is just by concatenating the two vectors. So let's say you did attention over French and attention over German. You could just concatenate the two vectors. You could add them together, or you could do something like hierarchical attention, where you do attention over those vectors and decide which one to use. So there's lots of different ways to do it, and that's what the middle paper there is talking about. Okay, so I will move on. There's a bunch of ways that people have proposed to improve attention in some way or another. These are, you might want to use them depending on your task. Like regular attention works pretty well, so you might not necessarily need to have any of these. But all of them kind of make sense, so which is why I decided to introduce them here. The first thing that a lot of people have noted is that neural models, when they're not trained very well, or when they're tested on words that don't, or tested on sentences that don't match the training data very well, they tend to drop or repeat content. So you get these translations where basically you have this long sentence that's translated into 3 words, or you have a sentence where you repeat the word nice to meet you, you, over and over and over again. So coverage models basically model how many times the words have been covered. There's a bunch of ways to do this. I think maybe the first way was proposed by Koehn et al. And the idea here is that assuming that we're doing a task like translation, in translation, we can assume that most of the words will be covered one time, will be translated one time, especially if we're doing something like English to another very similar language. So what they did was basically they added an additional loss term that said if each word in the source isn't translated about once, you pay a penalty. So this is a way to train the model to try to enforce this constraint. Another way to do this is adding embeddings indicating how many times you've covered a particular word. So basically you just add some other stuff into the model, and this will allow you to figure out how many times you've covered something. Which one should you use? The first one doesn't increase your parameters at all, so that's probably a good thing. But this won't work for anything where we don't expect each word to be basically output one time, about one time. So this probably wouldn't work for dialogue generation, for example, because dialogue has will have greatly varying length in the input and the output. Another thing you can do is incorporating a Markov property, and basically the idea here is that the attention from last time tends to be correlated from the attention this time. So if you look at this example here, you can see that it attended to the same word 3 times in a row, it attended to the same word 2 times in a row, and the same word 2 times in a row. So the idea is basically you use information about what it attended to last time when making the next attention decision. There's a bunch of different ways you could do this. This paper investigates one, and there are others as well. Like, actually, I didn't add this to the references, but there was a thing on recurrent attention, where basically you train a recurrent neural network to learn this for you. Another kind of interesting thing is bidirectional training. So you basically train 2 models. One model from, I guess this is Estonian to English, and one model from English to Estonian. And then you make it pay a penalty every time it doesn't match. So this penalty is the penalty over the trace of the matrix multiply here. So what this is saying basically is if things in the same position in these two matrices look about the same, you get a bonus. If you have very different matrices for these 2, then you don't get a bonus. This worked really well in this particular paper, but this requires you to train 2 models, 1 model in each direction at the same time. So that's a bit of a pain, I guess. You can also do supervised training. So the idea behind this is we get some gold standard alignments in advance, so we can either have somebody manually annotate our data set with proper correct alignments, or let's say we have some strong alignment model. Maybe we know that we have a model that tends to give us better alignments than we get from our attention. Then we can use this alignment model to kind of bias these. And what we do is we measure the difference between the attention and the alignment. Yeah. But one important thing to remember, this is something that I hadn't seen written in a research paper before until this paper just very recently. But it's something that almost everybody who's used an attentional model and visualized the results has noticed. But basically, attention is not an alignment between the words. Don't expect attention to look like alignment. One example of this is attention is often kind of blurred all over the place. You might see that it's attending to basically nothing. This is especially true when it's doing something like generating a word that has no direct, that doesn't correspond to anything directly in the input. So if you're generating a function word in translation, often there will be no function word in the input that matches this. Another example would be dialogue generation, where you're generating, probably dialogue generation will give you very fuzzy alignments all the time because there's not a very strong correspondence between individual words in the input and output. Another thing is attention is also very often off by 1. So this is a beautiful example of this. The blue ones are correct. The green ones are what the attention actually picked. Does anyone know why this happens? Yeah.
Initialize the state to 0, so you won't really be able to attend to the
What was the other opinion?
I was saying you encode the words, like you pay attention to the hidden states in the encoder, which is not necessarily aligned to the words. Like the hidden state at time t is attending to all the previous words and all the next word if you have bidirectional.
Right. So I think the initialization might have something to do with it, but I think the second answer, which was that when we have an encoder, particularly a bidirectional RNN encoder, each of the states has already seen all of the words in the sentence. It's just which one happens to be closer. So if you have an encoder over A, B, C, D, the state here has still seen information from B through its forward encoding. So there's not a really, really strong motivation for it to get the attention directly on the word itself, but it might get it one off like this. So yeah, this is something important to remember. So just because, let's say you did supervised training, of course you'll get a much higher alignment accuracy from your attention model, but you might not necessarily get better translations because attention is not alignment. Yeah.
But it seems as if there's still a tendency for the attention to be diagonally dominant.
Yeah, and the reason why is because recurrent neural networks don't just randomly put information all over the sentence. They like to put information closer to where they got the information. So it probably won't be 10 off. It'll probably be 1 off or directly on or something like that.
So does that supervised training help for the machine translation?
That's a good question. There are papers saying that it has helped. I have run experiments where it didn't help very much. So it depends on how hard you try, I guess.
So we can take that one off into account. Maybe somehow it would work out.
Yeah, maybe. So I don't know if supervised training helps. I have not gotten it to help myself, but a few other people have. So yeah.
Do people try to enforce the diagonal?
Yeah, there are ways that you can do that. I don't. There were ways that you would do that in original alignment models, but I don't think there are.
If you use like a Markov assumption and just attend to the previous words, that's automatically used for that kind of thing.
That would not necessarily be diagonal directly. That would enforce local consistency, but it might still be able to make big jumps. But yeah. I'll have to get back to you on that. I think there might be, but I can't come up with one off the top of my head. So there's also a few specialized varieties of attention that you might want to know about if you're doing something related to these things. So one is hard attention. The idea of hard attention is that instead of doing soft interpolation, make a 0-1 decision about what you're attending to. One thing to note is that this is much harder to train because you basically have 0-1 decisions which are not differentiable. And it requires methods such as reinforcement learning or something else like that. One kind of neat example of this, I don't think anybody has shown that this works better or that this works a whole lot better than a comparable soft attentional model, but one thing it might be able to give you is interpretability. So this is a neat paper where basically they use hard attention to highlight phrases in a document that were useful in making a decision. So this is a beer review that allowed where it tries to predict the look of the beer, and it says a very pleasant ruby red amber color, and this was used to predict the look. So even if hard attentional models haven't given a huge gain in many standard tasks, it's still pretty useful here.
So
Yeah.
if it's hard, why are there so many words?
So this is a 0-1 decision, but it's not necessarily, they're not taking the softmax here. They're actually taking a sigmoid, I think, which allows you to attend to all the words or not words. Yeah. Another thing is monotonic attention. This might be something to think about if you're doing something where we basically have things that are in the same order in the source and target. So for example, speech recognition is always the phonemes are in the same order as the input speech. You could also think of something like incremental translation, where you translate parts of the sentence at once. Morphological inflection. This is where you conjugate a word into another word. This is usually monotonic, but not always. Summarization also is usually monotonic, but not always. So you end up getting something that looks like this. This is a model that combines, this one I'm citing here is a model that combines monotonic attention with hard attention. So there you get kind of a thing that walks through the sentence in order. This is for morphological inflection, but they have some nice examples from summarization in their paper also. There's also convolutional attention. So this is an idea that is maybe not what you thought about at first. So normally when you heard convolutional attention, you might think that you were doing a convolutional network and then doing attention over that convolutional network. This is actually a different idea. And the idea is basically that when you decide attention, you also use information about the surrounding words. So it makes a lot of sense if, let's say you wanted to do something where you wanted to answer questions about people. And you might know that Mr. something is very often a person. The idea here is that when you make your attention decision, you also look at the neighboring words. So you can say, I want to attend to a word that's one next to Mr. Yeah. The context-sensitive word embeddings do capture that a little bit already, but this is a more direct way to take that into account, I guess. So, whether this is necessary if you have a very strong encoder, I actually don't know. So, but I thought it was a neat idea, so I thought it would be worth introducing. Another idea is multi-headed attention. So the idea behind multi-headed attention is basically that we have multiple attention heads, and each of these can focus on a different part of the sentence. So one example of this that kind of makes a lot of sense, I guess, this is in a code This is in basically a summarization paper. It happens to be on code summarization, where you try to guess a function name from the function itself. But the idea here is that you have this copy mechanism, and then you also have just a regular attentional model, and you use a different attention for each for the copy mechanism, which is in pink here, and the regular attentional model, which is in yellow. And you can see the regular attentional model is much more fuzzy. It's kind of focusing on the whole function, while the copy model is much more sharp, and it's focusing explicitly on variable names. So this has two attention heads, basically. It has one for the regular attentional model, one for the kind of copy model. And then there was another paper, which I'll talk about in a second, which basically does 8 attention heads. And these attention heads don't have any specific semantics on their own. They're just all kind of independently trained and can focus on different parts of the sentence. And this this is combined with self-attention, so you can note that the start and finish ones are the same. But the interesting thing here is that you can see some of the attention heads are focusing on more difficult, and some of the attention heads are focusing on making. So you get this kind of composition, multi-word expression, making more difficult, where each part of this is focused on by a different attention head. So the last thing I'd like to talk about is an interesting case study. This was a paper that came out very recently. It was accepted to NIPS apparently, and it kind of does a pretty different way of doing sequence-to-sequence modeling. I think many of you have seen this already. I've also already referenced a bunch of the things in my introduction to methods. But basically, this is a model that looks a lot like this. It has a bunch of layers where layers are using this multi-headed self-attention to basically learn word embeddings. And they're using this instead of the regular recurrent neural network. So one thing that's notable about this is this doesn't have any recurrent neural networks in it whatsoever. And it's just using this self-attention, multi-headed self-attention to learn all the context-sensitive stuff. It also has other things like extra feed-forward layers, which I'll talk about, and also layer normalization, various stuff, which I'll talk about later. A notable thing about this is it gave really strong results on standard machine translation datasets, and it's super fast to train. It's super fast to train because you don't need any recurrent neural networks, and recurrent neural networks are very slow to train on GPUs because they require you to step through the recurrent neural network. So this is kind of interesting. There was a question, I forgot who asked it, about how do we know about the positional information? So the way they handle positional information in this is you add an additional embedding to each of the words that basically is an encoding of its position in the sentence. So the first word in the sentence, if it's I hate this movie, you have the embeddings for I hate in this movie, but then you also have the embeddings for word number 1, word number 2, word number 3, and you basically just add these together to get the final embedding you use. So you get an embedding that basically represents the word I in position number 1 of the sentence. And then you can use this to learn things like words that are in similar positions should have more of an effect on each other than others. This paper is very unique in concept and it gets very good results. One thing you should be careful about is it introduces like 100 different tricks, probably all of which are important to get your model to work properly. Just a few of the tricks they do is they're using self-attention, like I mentioned before. They're using multi-headed attention. They're using normalized dot product attention, which are all things that I introduced. And then they're also using the positional encodings that I just mentioned here. So all of these things were kind of things that were partially, some of them were introduced in previous papers, but they kind of combined all of these together to get something that works quite well. Which is probably also why there are 7 co-authors on this paper. They had a lot of people working on this. They also have a bunch of training tricks. So they use something called layer normalization, which helps ensure that layers remain in a reasonable range. The output remains in a reasonable range. They have a specialized training schedule. They use something called label smoothing, which inserts some uncertainty in the training process. They also have a masking regimen, which allows them to do efficient training, where they basically train using the whole sentence at once. And what this looks like is basically, instead of having a recurrent neural network and then doing attention over only the source, what they can do is they basically calculate the source and target all the same. And then they have this masking function where basically in the first time step, you only look at the things in the source. Then in the second time step, you mask everything after I. Then you continue adding a mask that looks like this, where basically you mask out all of the words that you haven't already output. So by doing this, you can basically multiply this mask by the embeddings and then do your normal operations in a kind of like single big GPU operation, which is really fast to train compared to a regular recurrent neural network. So this is a kind of neat paper. This is one of the papers that I really liked recently. So if you're interested, you can look. But beware of all the training tricks, and don't think you can just go in and implement this all by yourself in a few days. So that's all for attention, I guess. Are there any questions or discussion? Stuff like
Have you tried this all attention already?
I myself have not run this. I know a lot of people who have run it, and it works quite well. If you use the official implementation, I know people who have re-implemented it and gotten it to work, but it takes a lot of work, which is why I'm mentioning this here. I think we're working on re-implementing it ourselves as well. So. Any other questions? Yeah.
If you have an encoder which works at the character level,
Yeah.
let's say for some language which doesn't have a
Yeah.
word, does attention make any sense? Because you would be attending.
Character level attention makes sense, but only if you have some context sensitive encoder. But in reality, all sequence-to-sequence models use some variety of context-sensitive encoders. So as long as you're using a bidirectional RNN or convolution or this self-attention thing with positional embeddings, you should be okay. And there's actually a lot of work that has used attention over characters and given very competitive results. So it totally makes sense. Anything else? Okay. If not, I'll finish up here and I'm happy to answer individual questions as well.